So this is section 9.9, functions represented by series. So what this is about is we talked about that these series can represent a function over the values for which the series converges. So for example, we know that the sum of x to the n, that's a geometric series, and it's a special case of the power series where the c sub n's are all 1 and the a is 0. All right, so it's also a power series and it's a geometric series. And we know that that's equal to 1 over 1 minus x because that's the a sub 1 over 1 minus r from geometric series. And we know that that converges whenever whatever the common ratio is, which happens to be x, is between -1 and 1. So absolute value of x is less than 1. So we have that formula. We want to think that this is a function, right? This is a function f of x. And this is a series, so we have a series that represents a function. Well, you can use that to get other functions. So for example, we can take this series and we can replace the x in this series with negative x. So we'll replace the x with negative x. It's basically just a substitution of negative x. Then I would have 1 over 1 minus negative x, which would be 1 plus x. And then over here on this side, I would just change everything that's an x here to negative x. So 1 is just going to stay 1. X is going to stay negative x. Negative x squared is still plus x squared. Negative x cubed is negative x cubed, and so on. All right, so what I can see that I have there is the sum from n equals 0 to infinity of -1 to the n, x to the n. So it's basically just the alternating series of that geometric series. Still converges on the same interval, but now I have a different series that's representing a different function, a new function. We can do other kinds of substitutions too. Like let's say we replace the x with, we're going to replace the x with negative x squared. Why negative? Oh, there we go. Why negative x squared? Because it's cool. That's why. So what are we gonna end up with when we do that? We're gonna have, instead of 1 minus x, we're gonna replace the x with negative x squared. So we're gonna have 1 over 1 plus x squared. All right. So what happens in this original series when we replace all the x's with negative x squared? So I'm going to have 1 is going to stay the same. This x is going to be replaced by negative x squared. This x squared is going to be replaced by negative x squared squared, which is positive x to the 4th, and so on. So this one's going to be replaced by negative x squared cubed, so it's going to be minus x to the 6th, and so on. And so now we can go over here and say, all right, well, what would be a formula that would describe that sum? It's the sum from n equals 0 to infinity. I can see that the terms are alternating, so let's put in a -1 to the nth power. And then how am I going to get this at the top? Well, if I'm starting at 0 and I think about, this is 0, 1, 2, 3, then the power of x is just n, it's 2n. So instead of x to the n, I have x to the 2n. So now I have another series, 1 over 1 plus x squared, that's a different function, is represented by this other series. So basically I can manipulate everything we're doing here, starting from this one geometric series, we'll manipulate that around a lot and get different things. So another thing we can do is take a series like this and just multiply both sides by, let's say, x cubed, right? So I can just multiply this one times x cubed. And then what I'm going to have over here is x cubed over 1 plus x squared. What I'm going to have over here, did I want to do that one? Well, we can do that one, I guess. We can do that one. All right. I had originally planned to go back to here to get this, but you can actually do this to any one of these series. I chose to do it to this one, multiplying times x cubed, but we could have multiplied this one by x cubed using the same process. So then what I'm going to have here is I can just multiply all the terms by x cubed. So I'm going to have x cubed minus x fifth plus x seventh minus x ninth plus etc. All right, so that is equal to the sum from n equals 0 to infinity of, let's see, it's alternating again, so I have -1 to the n. Pay attention to, like, you're going to see the book plays around a lot with, did we start at n equals 0 or n equals 1? And you can actually do it either way and just sort of adjust what your formula is to compensate for whether you started at 0 or 1. So if I'm starting at n equals 0, then my first term in this case is going to be positive. So I think about that. Then I think this is going to be n equals 0, 1, 2, 3. Of course, I could do 1, 2, 3 and then adjust the formula over here if I wanted. But if I do it this way, I get that it looks like I have x to the, let's see, what do I have to do to 2 to get 7? I do to 1 to get 5. I'm going to go times 2 and then plus 1. Let's see, actually, if I think that I'm just taking these ones and adding 3, and that was 2n. So it should be 2n plus 3, right? So 2n plus 3, 2 times 1 plus 3, 2 times 2 plus 3, 2 times 3 plus 3. Yeah, that works. So it's x to the 2n plus 3, which also illustrates how you sort of have to think about that formula a little bit. All right, so now I've come up with 4 new series representations of different functions by doing substitutions, by multiplying by something. And the next thing we're going to find out is the very cool fact that you can also differentiate and integrate these things.